I need permission to share screen.
Yeah, sure. Sure, I will give you a permission right now. Just a moment. Uh, uh, just please give a permission.
Yeah.
Recording? Okay. Okay. Dear colleagues, we're happy to see Professor Louis Kauffman again. And today he will tell us about the Temperley-Lieb algebra and visualization of meanders and projectors, idempotents. Let's welcome.
Thank you, Vasily. It's a pleasure to be here. So, I'm going to talk about the Temperley-Lieb algebra and mostly about the multiplicative Temperley-Lieb algebra, which is defined formally as you see on this slide. Um, we have generators U1 through UN minus 1 for the n-strand algebra and an identity element, of course, and an element of a ring, a commutative ring, delta. And then the relations in the algebra are by definition that ui squared is delta ui u j ui is equal to ui if j differs from I by 1, and ui uj is equal to uj ui if the difference is greater than 1. This algebra arose in statistical mechanics originally, um, and implicitly actually in the kind of projectors that Dirac used, uh, but it was formalized in this form by Temperley and Lieb, and they gave matrices that satisfied these kinds of relations that were related to transfer matrices in statistical mechanics models. In fact, Temperley himself investigated the algebra a lot, and he found a braid group representation of this algebra, but he didn't do anything with it. But later, um, Jones found the algebra again in a somewhat different context that's related to physics, the Jones Tower construction, which I won't go into. And he got very interested in the fact that there is a braid group representation of the algebra. He found one. We'll talk about that in a moment. And uh, and he was able to put a trace on that representation, put a trace on the Temperley-Lieb algebra, rather, in such a way that he could define, using the Markov theorem, an invariant of knots and links, which is now known as the Jones polynomial. What I'm going to be talking about is combinatorial and diagrammatic visualizations of this algebra. And I will just talk a little bit more about the background here. Maybe we should do a full screen view. Let's see if we can do a full screen view. Yeah, that's probably a little larger for you. So, pass one on diagrammatic interpretation of the algebra are these diagrams. Excuse me a moment, I'm moving something on my screen. There we are these diagrams, which are like braiding diagrams, where we define UI to be like a braid. It involves the I and the I plus first strands, and instead of crossing over one another, they form a cup and a cap, a maximum and a minimum. By the way, I apologize to people who understand this for many, many years and know all about it. There may be some things in the talk that you don't know, and I thought I would best start from the beginning. So here we're at n equals 3, and we have two generators, U1 and U2, and you see they are cups and caps in the first and second line and in the second and third line, and there's the identity, and the loop is uh, corresponding to that scalar delta. And then if you multiply by attaching the lower strands of one element to the upper strands of the next element. That's the composition. Then you find that ui squared produces a loop, and so ui squared is delta ui. And if you form ui, uj, ui, where j differs from I by 1, like u2, u1, u2, why then you see that the cups and the caps conspire to give you a line which goes all the way down from top to bottom, and and topologically is the same as a vertical line, and so ui, uj, ui is equal to ui. Um, and 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 so the relations in the algebra are happening. And of course, if you separated UIs defined this way by more than one, why then they will commute, as is in the box with U1, U3 at n equals 4. So all of those relations are realized by these pictures. And we want to see what we mean by these pictures combinatorially, among other things, but just play with the pictures for the moment. If you take U1, U2, then you get another element, which I could write like I have without, by just indicating who's connected to whom. And that's the main point here, that what these pictures are doing is they are connecting lines either from top to bottom or from top to top in such a way that the lines do not intersect in the plane. Such pictures can be matched up to so that you pair maxima and minima and written therefore as elements in the Temperley-Lieb algebra. But so if you were to draw U1, U2 and then straighten the line a little bit that's in the middle, you would lose a maximum and lose a minimum, and you would have this connection picture. Similarly, U2, U1. So now you have a closed algebra. If you want to play, if you hadn't thought about this algebra before, this is the simplest non-trivial one. You have U1, you have U2, you have the identity, and you have alpha, and you have beta, and then if you care to try multiplying them together, you'll see it's closed up to the scalar, of course. Uh, Now, continuing about background here, um, this is, let me see. I thought I skipped something. No, I didn't. All right. So continuing about background here, what does the representation of the algebra look like to of the braid group look like? Well, the
No,
represent
excuse me. If we have, mm, uh, can we try to get something like parity for the temporal leaps? Can we try to make it virtual and create parity to get a parity bracket or something like that?
Well, of course, one always asks that question now, and the answer is certainly you can define everything that I'm doing in the virtual category, and then you have virtual crossings, and you have virtual Temperley-Lieb algebra, um, and you can track parity when you're working with virtual knots in various ways. So certainly you can. You know that already, right?
Okay.
Yeah. But I was just going over basic background. Um, the representation of the braid group goes as follows. You take a braid and you turn it into a linear combination of a Temperley-Lieb, the ith braid, into the ith Temperley-Lieb element and the identity with appropriate coefficients. So the way I like to do it is to write it this way because it corresponds to the bracket polynomial expansion. But but this is essentially the way Jones defined a representation of the braid group. He's defining it without having the pictures in the background. Um, so he understood that if he tried to do a linear combination in that form, he could adjust the coefficients in such a way that he got a representation of the braid group. This is a correct adjustment of coefficients. If you take A and A inverse like I just did, or and the value of the loop to be minus A squared and minus A to the minus 2, you can verify you have a representation of the braid group. And then there's the matter of the trace. At the diagram level, the trace is as follows. You close the braid in the standard way and take delta to the number of loops in the closure. Now, that's a nice simplification of what Jones's trace, which was defined in terms of the algebra itself. And we'll come back to that. But this
Excuse
way
me,
of,
Lou, but we know that the Kauffman bracket does not detect links. Doesn't it follow from that that this representation is not faithful if the
no,
bracket?
no, it doesn't. The problem is this representation faithful? That's why I put the problem in front of you, but it doesn't follow from the non-faithfulness of it does not follow from the fact that the Jones polynomial can see two links as being the same. It
Okay.
doesn't. But it's a nice question, right? You could look at that, whether or not this representation is faithful. People have, of course, but I don't have an insight into that. But now the bracket polynomial, I remind you,
Map it
is
towards
this visible on the screen? I have little obstructions on my screen, but I think you don't. Um, the bracket polynomial um, is actually paralleling the braid group representation, but you're expanding a crossing anywhere in the diagram in the same way if it were vertically arranged so that this was a UI and that was an identity, which it isn't in general. It's just two ways of smoothing the crossing. Um, so you smooth the crossing in the two ways and use a convention to associate A to one of them and A inverse to the other, and you multiply by the loop and expand this, and you get an invariant under the second and third Reidemeister moves, and you get an expansion over states where states are smoothings of the diagram, and you check at each smoothing whether it's an A or a B, an A or an A inverse. I call B the one that would be A inverse, and you take the product of those weights and delta to the number of loops in the state. Sometimes we normalize it with one less loop, but the point is that the polynomial is a sum over all of these terms, which have no signs in them. The signs are coming from the minus sign in the delta, so that when you multiply it all out and expand it, you can possibly get some cancellations, as you would, for example, if you took a link here like this and expanded it, that it's an unlink, then you will expand it and get a number of states, and you can't see the cancellation here. But the fact is that delta is equal to minus a squared minus a to the minus 2. And when you put that in and add everything up, you get a complete cancellation. And this looks like the unlink. Well, that happens, in fact, for certain non-trivial links. First example, due to Morven-Thistlethwaite. And how those cancellations are actually happening is a mystery. So Vasily's question is right on target. We do know there's some loss, some kind of cancellation can happen, at least at the link level, and we don't know whether it cancels all out at the knot level implies that the knot is unknotted. We don't know that. Those questions are somehow related to that question about the braid group representation, but it's not obvious. So that's the background. But what we're going to look at here is very elementary things. We're going to look at the multiplicative algebra itself from the point of view of the planar connection algebra, which I just introduced to you as diagrams, but now I wish to introduce it to you again as a combinatorial structure. You have a row of points, you have another row of points, and you consider all connections between them that either go top to top or top to bottom or bottom to bottom that do not cross in the plane, planar embedded connections. And planar embedded connections are closed under the composition that we mentioned. Um, and, uh, and so you have a combinatorial algebra there. And you also have a category or categories because you could perfectly well have somebody which has 3 points at the top and 1 point at the bottom, for example, and draw connections of that kind. So in general, if you had n to m, then if you have n to m and m to p, then you can multiply them and get n to p. An obvious remark, but useful for thinking about how things behave. So let's look at alpha again now, thinking of it that way, and square it. So I've squared alpha. You see, alpha is the top here, and alpha is the bottom here. And again, a line goes from top to bottom that can be simplified and is by definition simplified in the monoid because we're only interested in what points are connected. So this is equal to alpha. Alpha squared is equal to alpha. We have an idempotent here. Um, and where did this come from? Well, if you look at it, you see that in the category, alpha factors into an A and a B, where A goes from 3 to 1 and B goes from 1 to 3. And if you look at the reverse product of A and B, the A, you see that it's the identity. That's the wiggle in the middle. And what are we saying? We're saying, I should have put it in this slide, and if I didn't put it in the next one, I'll put it on my uh, whiteboard. No, I put it here. Good. So here's another example. The point is that if I can factor the identity, then I can put the identity, I will then get an idempotent. So I can get, once I understand that idea, I can construct lots and lots of idempotents. For example, here's a factorization of the identity which goes from 1 to 5 and back to 1. And if you write it in the opposite order, AB, then you get this Temperley-Lieb element, this connection algebra element, and the square of that will reproduce the wiggle of the factorization of the identity in its middle, which collapses, and so p squared is equal to p. But it's very general, and you needn't have diagrams to understand this. If in some category you had a factorization of the identity, then you could define the opposite product as p, and then p squared will produce the factorization of the identity in the middle of it, and that's the identity, and so it goes away, and you will get p squared is equal to p. So that idempotents will happen in any category where there are non-trivial factorizations of the identity. And so we can look at a lot of factorizations of the identity, and therefore we can look at a lot of idempotents in the multiplicative Temperley-Lieb algebra. And what we've done is we've seen them now up there in the connection algebra, and you could be curious, how are they appearing in the actual Temperley-Lieb algebra? Because we left it and went to the connection algebra. So it is a theorem, and I said we shall prove, but I'm only sketching here as far as that theorem is concerned, that the Temperley-Lieb monoid is isomorphic to the connection monoid. Um, but mm, the rest of this slide is repeating. Okay, so I don't want to run ahead of myself, but how am I producing factorizations of the identity for the Temperley-Lieb category or for the connection category? Well, what I'm doing is I'm taking a line and I'm I'm choosing a point on one side of the line and I'm taking a walk and I cross the line and back and forth and eventually I come to the other side of the line. Such a thing is called a meander in combinatorics. The line is important and, of course, gives us two algebra elements from our point of view in the connection algebras, one going from 1 to n and the other going back from n to 1, and that's a factorization of the identity. So meanders of this type, starting on one side of a line and ending on the other side of a line, are factorizations of the identity. Um, and I just wanted to say that you can then make various kinds of meanders. Um, and in fact, let's just go off and draw a picture or two. So one way to think of meanders that are relevant to us is you wander back and forth across a line. Another way is you draw a Jordan curve in the plane somehow, and then you cut that Jordan curve with a line, and then you get a meander, a closed meander. And here I have an open meander. And just so you might wonder, well, how can I enumerate these? And to my knowledge, there isn't a good systematic enumeration of all closed meanders or all open meanders where the structures on the bottom and the top are arbitrary. But on the other hand, if you want to consider very simple meanders like this one, where you have a nest at the bottom, a nest, you know, like that. I'll call that a nest. Um, at the bottom and anything at all on the top, then that one is not hard to enumerate. And so it's amusing to see what you can do. I'll show you how to enumerate these. What shall we call them? Um, um, nested bottom, nested bottoms. So we'll call these NB meanders. Not that I need to use them later particularly, but I just wanted to do a little exercising with meanders with you. So this one, there's a nice way to enumerate them, and you might try counting and so on. Here's how.
It reminds me the Thomson algebra that Jones invented.
It reminds you of what?
Thomson group that Jones invented.
Oh, yeah, Jones didn't invent the Thompson group, but he related the Thompson group with knot theory and some other things. Yeah, maybe it is related to the Thompson group. Hmm. We could think about that.
Okay.
But I was just going to do something very elementary here. Let's enumerate these. So here's the simplest possible nested meander, the simplest possible closed meander altogether. Now here's what you do. You go to the top and you cut off an arc. There's only one way to do it here. I have a horizontal line. And then you take that arc that you cut out and you put it down on the bottom by taking it all the way around and bringing it back up, thereby producing a nest of size 2. That's the only meander with a nest of size 2. But now it branches, and we'll go to one branch because I could, you see, cut an arc off this one and put that all the way around and come back. And now again, it branches, and I could I'll just work on this one and keep making more complicated ones. So now I take this one and I bring that all the way around and come back. My pen is behaving, and so on. And so you see that you can produce all possible nested meanders by this method. Okay? Now, the interesting thing is that actually you are producing everything this way if you want to think of it in a certain form. Namely, you could go to the middle of it like that, you see, right? There have to be an even number of crossings. You could go to the middle of it like that, and you could contract this and put this on the bottom. So up on the top, you have what's on the left, and then on the bottom, I will take
Excuse me,
what
and what's the induction procedure? If you have all meanders of one length, how do you?
I said that you take your meander, which is a nested meander, and you choose an arc that is available to the outer region,
Yes.
and you cut that arc. Let me do it one more time on a copy so that I don't disturb the example that I was already working on. There. Okay. So I'm going to concentrate on some arc that's available to the outer region, and I cut it. And then I take that and I replace that arc by one that goes all the way around through the bottom and back to the top.
It looks like a stabilization of a braid.
Sure, it does, yes. Um, and if you do that, then you will go from a meander with, in this case, four a four nest to a five nest. And if you think about this for a while, you'll see that you are actually enumerating all possible nested meanders. The other remark that I'm making is that if you take a nested meander, then you can think of it as a combination of two parenthesis structures. If you think of the upper and lower parts as parenthesis structures, um, by cutting it right in the middle and then contract this. So you see I have the left side and I have the right side, and I'm going to put the right side all the way in the bottom by contracting it. Yeah? And now I get an
Maybe
arc.
maybe you remember that a very long ago I was constructing knots by double bracket structures. I was using something on the top and something on the bottom, and I constructed a bracket
Mm,
semi-group of knots. It seems very
sure,
similar.
sure. These are very general ideas which apply in many cases with whenever we're working with this kind of geometry, as it were.
Okay.
Um, so I am not at this stage talking about other subjects. I'm just talking about playing with meanders. And the point I'm making is that this construction, cut the arc and bring it around, that enumerates nested meanders. So that's an enumeration that you can understand. But then if you then regard a nested meander as a kind of product of two parenthesis structures, then you can think of it as an ordinary meander. In other words, whenever you have a nested meander, let me use another color on this one, you can think of cutting it from top to bottom and let's see, one, two, three, four, five. You can sometimes, excuse me, You can sometimes think of cutting it from top to bottom if there is a left half and there is a right half. There may not be a left half and a right half, and it may not factor. So then you're not completely enumerating meanders. So there are lots of puzzles here that are very interesting, and there's a literature on meanders already existing. So what we're saying is that these meanders are closely related to idempotents. So now let's go into that a little more carefully and see what's going on with that. I think I will let go of that slide. All right. So let's suppose that let's do another example. So suppose that I take um, this guy. Okay. And I write correspondingly to this guy. Oh, he's not so interesting. I'd rather do a different one. That's a little more interesting. So this is the B and the A, and I want to write the AB. So that's this. And I'll call it P. And we'll have that P squared is equal to P. It will be, because the wiggle will occur in the middle and it will work out. Now, what is this in the Temperley-Lieb algebra? So we need to go from the connection monoid to the Temperley-Lieb algebra. And there's a nice way to do this. In general, you could do this just by hand. You need to pair the maxima and minima. So in the case of this small one, you could just look at it and you would say, aha, I need to have a minimum that corresponds to that, a maximum that corresponds to that. And then I'm going to pick up these two minima, and this one ought to be paired with the guy on the bottom. On the other hand, this is coming on down, and it ought to be paired with that other one, and then this one will come down in the middle, and this is paired with that. And so I can map it to U2, U1, U3, U5. On the other hand, there's a general procedure which lets you do this automatically or in general and gives you a canonical element. And I want to show you that so that we can use it to play around. And the general procedure is as follows. Write this in a completely rectilinear way. So I have 5 points. And I have the rectilinear version of that connection, the rectilinear version of this connection. And now I have 5 points at the bottom. And this one goes straight down, straight over, and drops into the middle. So in general, a line from top to bottom will go straight down, and then it will either go to the left or the right and drop into the point that it meets at the bottom. And then we have the bottom ones. Okay, so you convert it to a rectilinear one, and then the pairings are automatic. You go down the columns in between the points and pair as you go on down, like that. Pair, 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 and pair. Of course, in a more complicated example, it would look more like this. There would be some things. and you would be going down the columns, and you would pair that, and then you would pair this, and it would be parity, and you would pair the last one, and that kind of thing would happen like that. But here, there was only one pairing in each case, and we got a U2, U1, U3, and U5. So that's a general method for obtaining a canonical element in the Temperley-Lieb algebra from an element in the connection monoid. And in fact, when you do that, you get something that's in a normal form. That is the normal form that was invented by or discovered by Vaughan Jones for elements in the Temperley-Lieb algebra, descending products like this, 3, 2, and so on. I have other examples to show you, but let's continue playing with this because what we want to see is how it happened in the Temperley-Lieb algebra that this guy was a projector, was an idempotent. How did he end up being an idempotent in Temperley-Lieb? Well, you can do that. Yeah, the exercises are there. Well, the reason I go through this is because I think it's quite opaque uh, from the point of view of the Temperley-Lieb algebra itself, why such things are idempotents. We can see immediately that they're idempotents if we see that they contain a factorization of the identity in this way, but that involves going up to the connection algebra. If you were staying in Temperley-Lieb, you could, at the very least, do the calculation. Let's see what the calculation looks like. So you have U2, U1, U3, and U5, and you're multiplying it by itself. U2, U1, U3, and U5. And now you realize, now we're in grade school, and the grade school is that these numbers with U's attached to them, they commute as long as the numbers don't differ by one. And then we have basic identities like U2, U1, U2. Now look at this one. It commutes all the way past these over here. I made a mistake, didn't I? Wait. No, no, I didn't. I didn't. But I'm misleading you by drawing that line. But all you need to do this is use the only relations that are available to you, and the relations available to you are commuting and UI, UJ, UI is UI if J differs from I by 1. So look at this one. Here's U1. It passes by 3. It passes by 5 and ends up over here next to U2. So I'll write it out. U2, U3, U5, U1, U2, U1, U3, U5. But U1, U2, U1 is equal to U1. So I get a reduction. And now, what else can I do? Um, let's see.
Are you missing a U1?
This U1 can go over here. Oh, oops. Sorry. What were you were about to solve my problem? What do you want me to do?
Um, what should that be a U2 instead of U1?
Yeah, no doubt. Where?
Where the
U2,
U1 is.
let me see. The element is U2, U1, U3, U5, U4. Oh, that's the mistake. Um, that's a U4, not a U5. There is no U5, right? That's 4. 1, 2, 3, 4, 5, and the last one is U4. So this was a U4. Let's make our writing clear. That's a U4 there. And that's a U4 there. Now it will solve itself, assuming that I didn't make any other arithmetical errors. I deliberately chose this without having prepared it beforehand because they're easy, but I may have gotten myself in trouble by making little errors. Let's make sure there aren't any errors here. 2, 1, and 3 and 4, right? 2, 1, 3, 4, 2, 1, 3, 4. We brought the U1 over here and we have U1, U2, U1, which became U1. And we had a 2, 3, 4. And then we had on the other side, U2, U1, U3, U4. And why did now I'm looking for a simplification of this. But U2, U1, oh, and I kept it. U2, U1, U1. U1, U2, U1 is just U1, and here we are. And now we're looking for another simplification.
I'm sorry, is it U5 in the last string?
Oh, that
The
was a 4. Thank you. Yeah, okay. Now we're good. The U4 we should be good. Yeah, of course. So the U1 commutes with the U4. And then you have U4, U3, U4. And that's U4. So this is equal to U2, U3, U1, and then U4, U3, U4 is U4. And now we're done, but perhaps with a slightly different order. Our original one was U2, U1, U3, U4, and here you have U2, U3, U1, U4, but those commute, so this is U2, U1, U3, U4, and we proved inside the algebra that p squared is equal to p. So if you encountered some element in the algebra and found out that p squared was equal to p, doing it inside the algebra, you would be involved in that. Um, just the simplicity of commuting until you bump into something that's one away from you, and the basic relation. Those are the relations that have topological meaning, but it's not obvious how you would characterize such sequences if you were only looking in the algebra. If you go up to the category related to connections, then what's going on is very clear. But to enumerate them is to enumerate meanders, and that's hard. So I think that's interesting, and that's the main
By the way,
point.
don't you have idempotents which are linear combinations, not just
Yeah, we'll get to that. All right. So let's skip this. So here's a slightly more complicated example of this rectilinear method. I'm not going to calculate with it, but you'll notice that if you have a more complex entity, then when you make it rectilinear, you get sequences of descending products like this, and that's what I'm indicating. That's called Jones' normal form. Jones found that he could put every element in the Temperley-Lieb algebra into certain products of descending elements like that, and they are occurring quite naturally when you're using this geometry. I'm skipping remarks about oh, I'm skipping remarks about trace that I could make. So now I just want to mention some other things that you can play around with. For example, you could consider infinite products if you wanted to, because you could think of things like this going off to the right. Um, and then you could factor that. You see, if I wrote that as a product of Temperley-Lieb elements, it would be an infinite product of Temperley-Lieb elements because there are an infinite number of pairings. Each one demands another pairing, demands another pairing. It would be the product of U1, U2, U3 forever. If you squared it, then you will find that you could work with the infinite algebra and square it, but then you will have the interesting situation of passing an element across an infinite product of elements, which you're allowed to do by my definitions here that I didn't write. See, I have an infinite product here, U1, U2, U3, and another one, U1, U2, U3, and I want to simplify it. U1 is U1 is smaller than all of these until it bumps into U2, where it has to stop. So it can commute with this infinite product and end up over here. And that corresponds diagrammatically to exactly what will happen when you multiply. So you can play with that. I'm not going to play with it further. Here's another result. Suppose you have an element in the monoid, and you consider the powers of that element. What happens? If you have an element in the braid group and you consider powers of that element, it goes on forever. But what you will find if you try that, take an element in the monoid, a picture, and start looking at the powers of it, that eventually you will get to one so that when you multiply it one more time, it will give you that same one, p to the n, multiplied by some power of the loop. So it truncates. It truncates, and we end up in projectors after a while. And the proof is not hard. I think in the interest of time, I just indicate to you that what I'm going to think about when I have factored the original one, I have to think of factoring the original one and what kind of lines go between it so that it is factored in the category from n to k and from k to n for some k. And then examine what happens when you square that and watch, and you can prove this. I give you an example rather than proving it. Here's a P, nice P, with a cup here, and then a lot of connecting lines, and then a cap down there, all right? If you square it, these are all on the slide. If you square it, you see some of them pull up, and you get 2 and some lines. And when you cube it, you get 3 in a line. And by the time you got to the cube, then you got something which is an idempotent. So you either end up with an idempotent or you end up with some projectors if you keep taking powers of elements in the monoid. Now, you can do other examples. I was making up a curious factorization here and then trying the powers of this P. And you will see that as you keep multiplying it, eventually you'll get certain lines that go from top to bottom that simplify. You end up getting to projectors or idempotents after a while. Now, as Vasily was asking a moment ago, we're familiar with projectors and idempotents also that are written in the additive algebra, and they're important for topology. And these Jones-Wentzel projectors, for example, are linear combinations of all of the different elements of the Temperley-Lieb algebra at that level. So if I wanted the 3-strand projector, I could say, well, I want a linear combination of all of these elements in the algebra, and then I want it to satisfy some conditions. So, for example, you might take the condition that you want it to satisfy as that it should square to be itself and that it should annihilate all the UIs. That's the condition that gives you the Jones-Wentzel projectors. And then there are very nice recursion formulas for the Jones-Wentzel projectors.
Excuse
But
me.
I don't have a general
excuse me, Jones-Wentzel is used for constructing invariants of three manifolds. Can we use other projectors to get invariants under Kirby moves? And is it possible to use other projectors in the Temperley-Lieb algebra to get invariants of three manifolds?
A good question. I don't know. We've held on to the Jones-Wentzel projectors um, for dear life because they do so much for us. Um, but I have had the question of what will happen if we're in the virtual category, because then you could still have the Jones-Wentzel projectors, but you will have other behavior because of virtual crossings, and so you can try to get different projectors in that category to get generalizations of the invariance of three manifolds. Most of that is still not working very well. You can do some of that up to a point, but it doesn't give you a really good theory of somehow invariance of three manifolds related to virtual knots and links. Um, but some people like Scott Morrison have written papers about the combinatorics of this is the usual recursion formula for Jones-Wentzel projectors. Um, and Scott Morrison has a paper. I should give you the reference for it, but he shows that these elements that I was just showing you, which have nice powers, um, he can represent the Jones-Wentzel projectors entirely in terms of these elements. So he gets a reduced formula for the Jones-Wentzel projectors that's very pretty. Whether it has some good applications for the manifold invariants, I don't know. Um, but I think that the fact that we now understand a little better, or at least I feel like I understand a little better what's going on multiplicatively in the Temperley-Lieb algebra, that may help to understand what's going on with the projectors. And of course, the projectors get combined into evaluations of various sorts that are related to many questions about invariance, colored Jones polynomials, and so on. Um, so, uh, so this is just pointing at some of the things that are of interest to us that maybe these elementary arithmetic remarks that I've given you today may have some use. I think the elementary arithmetic remarks about the connection monoid that I've told you about are are interesting, and they relate to combinatorics, and they can be understood at the grade school level of things, and so it's fun to play around with them. But I would like to use some of this information to interface with the more complicated constructions that we've been involved in. Um, Notice that everything I said, it just depends on factorizing an identity in a category, so it will apply to other things. For example, a classical connection monoid is the Brouwer monoid. That's the complete connection monoid. You are allowed to connect top to bottom, or bottom to bottom, or top to top, and the lines can cross, and you take it up to topological pictures. You can draw it as topological pictures. That Brouwer monoid has been around since, I guess, the 1930s in relation to representations of the symmetric group. And and you could factor an identity in interesting and complicated ways. Here's a factorization of the identity, right? And it's a little Brouwer connection category element on the top and on the bottom, and if you put them in the opposite order, here's P. And P squared is equal to P because this is just a connection from top to bottom. So in the same way that we're understanding idempotents in the Temperley-Lieb algebra, we're understanding idempotents in the Brouwer monoid. Um, and it's interesting to play around with that. And I want to end with, and it could be in tangle categories as well. Let's point that out. Um, Suppose that I make a doodle like this, for example, and I cut it, and then I draw a tangle. Oh, that's not so interesting. Um, yeah. What I just drew is indeed a little unknown. Okay, uh, so played the same game, and I have a tangle here, and the square of that tangle is equal to itself, right? So, so you can build idempotents in all the categories you know if you feel like doing so. And what will be the consequences of that? I don't know. Um, but I want to point out that the generality of the remark even takes us out to things like self-replication in DNA. Let me tender persuasions and we'll stop. Remember how DNA reproduces itself. DNA consists of two strands, which are connected by bonds. And so you have a Watson strand connected by bonds to a Crick strand. And enzymes cut the strands and pull them apart. And you end up with, in principle, but this only happens locally, Watson, Crick, and the environment between them. And the environment is like the identity in the category, and the environment is able to factorize into a Crick strand that is attached to Watson and a Watson strand that is attached to Crick. And so the DNA reproduces. It's like this, right? Here's the DNA. The enzymes pull it apart, and then in the environment, deposits of molecules connected to one strand produce the double strand up here on this one, and the double strand on this one. Of course, they're interwound with one another, and there are topological problems about getting them apart, and so on. But the general schema is that you have Watson and Crick bound together. They come apart. The environment provides a Crick and a Watson. And so the environment is like the identity being factorized into an appropriate thing, which gives you the reproduction. And if you were to think about what we were doing backwards, here's P, and you pull P apart, and then you have the environment here, and the environment, the topological environment, miraculously produces the appropriate factorization of the identity, the cup and the cap that are needed to build another P, and then it gets cut apart and it reproduces itself. So I'm not saying this happens in biology. What I'm saying is that the scenario of a category in which something that you're calling the identity can be factored into an appropriate entity and thereby producing a new elements, that idea goes across in many, many different contexts. Um, Another example of a context in which that happens is the following. If you're in quantum mechanics and you want to know what is the amplitude for going from A to B, um, then in quantum mechanics you say, well, but what if there was an intermediate position and I think about all these different CIs that it could go to, C1, C2, and so on, um, and then it could go to B, and so the amplitude for going from A to B in Dirac notation is equal to the amplitude for going from A to And then here we have the sum over possibly going to CI and then going from CI to B. And this is a factorization of the identity. You have that the identity is equal to this um, summation. And so you can put that in and you get the sum on I of A, CI, CI, B. And this is the beginning of the path integral. That the amplitude for going from A to B is equal to the sum of the products of the amplitudes of going to all the intermediate stages. So this idea about idempotent in that sense is 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 uh, is a piece of general nonsense which can land on a lot of different things and maybe sometimes illuminate them. I'll stop here.
Okay, thank you very much. Are there any questions or comments? Remarks? Well, okay, thank you very much again. We hope there will be a lot of discussion afterwards. So that was a great talk. Thank you.
Thank you.
Ну что, коллеги, давайте попьем чайку и поговорим о наших